Hey guys, today we're going to be looking at um, double integrals in polar coordinates. And the example that I'm going to show you is telling us to use polar coordinates to find the volume of a given solid, and they're giving us that it's a cone. Z equals square root of x squared plus y squared, and it's above a disk that is x squared plus y squared less than or equal to 4. Look at all these x squareds and y squareds. That's telling you that it should be done in polar coordinates. It would make your life a whole heck of a lot easier. And a good way to start off with these kinds of things is to draw the region and see what it looks like, so you get an image of what it should be. So here's our three axes. The disk is a circle on the xy coordinate, xy plane, ranging from 2, -2 over here, all the way around. And then the cone, just a normal cone. And the area we're looking at is the area under the cone and above the plane. So it's this solid, if you swing it around, the solid vessel. Now what we want to do is figure out the volume of it. And the best way to do that is a double integral, as the problem tells you to do. And first, we need to figure out what the function is we're going to integrate. So we're given the cone, z equals x squared plus y squared. To convert that into polar coordinates, we know that x equals r cosine theta, so x squared equals r squared cosine squared theta, and then y squared would be r squared sine squared theta. So when we simplify that down, we get r equals square root x, z equals square root of r. That's our function, and that's going to go in here. Now we have to integrate. Usually when we're doing normal coordinates, it's dx dy, or dy dx. When we convert it into polar, it's r dr d theta. I'm not going to go into how that's derived or what that means, but that's what we have to put here. And I've already forgotten to put the r. Okay. Don't forget that r. Next, we have to figure out our limits of integration. And in polar, it's usually easier to put theta on the outside and r on the inside. And theta is pretty easy to figure out if you know the polar coordinate system. It goes from 0 to pi and then back to 2 pi. So we know that since we're dealing with a volume, we're going to go all the way around this circle, back to the origin, back to the beginning. That whole area, so that would be 0, and it ranges back all the way around to 2 pi. R is our radial arm length, and for this problem it's constant. It's always the length of 2. So no matter where you are in the circle, it's always 2. So from 0 to 2, from the origin to 2. Next, we have to solve it. And I'm just going to show you quickly how to do that in case you've forgotten or you get stuck. Happens to me all the time. So we're just going to rewrite this, and square root of r squared is r. So r times r equals r squared dr d theta, and we solve that. We're interested in just the inner integral right now. We're going to deal with the outer one once we're done. But to find that, we integrate, and we get r cubed over 3, integrated from 0 to 2 d theta. And when we get that, we get integrate from 0 to 2 pi of 8/3 d theta. Then we integrate that, and we get 8/3 theta from 0 to 2 pi. And our final solution 16 thirds pi. And that's how you find the volume using double integrals in polar coordinates.